Uh, so I think I was muted for some time. So let me just go back and repeat what I've been saying. Okay, thank you, because I was going to spend an hour recording and going to hear me. So I was saying that I have marked most of your scripts for the first homework assignment. Most people seem to understand the work. The only scripts that are left are those who submitted late. And then the other thing was that the memo is already on Click UB, so you can have a look. It's just that there was a typo. I think one of the problems, I think I wrote X instead of X over A, but the final answer is correct, because you just have to look at the dimension. So I think the first answer had to be V over 2. Just look at the dimensions. So if you had maybe put a wrong A somewhere, or when it was missing, you might have gotten V A0. And this is clearly wrong because of dimensional analysis. V naught already has the dimensions of energy, so you cannot add. If this was high school, it would be like you saying that the units of the term that you've added would be joule second or joule meter, because A0 has the dimensions of A. So, but everything in the memo seems fine. The semester test date, I think everyone has agreed that we will write that on the 1st of July. And the last thing that I needed to mention before we begin was homework assignment 2. So I was thinking to give it to you, to release it on Friday, maybe by midnight. Or do you want it to be released today? Because I thought that maybe most people will be writing the statistical mechanics test and they might not want to start the problems. But it's due in a week time. Whether it be released today or Friday. So homework assignment 2 will be covering chapter 8, the variational principle. So I will give you some trial wave functions for you to try out, and then just check that whatever you get. So no one is responding. So I guess this means that you will get the assignment on, maybe someone did. Okay, so I'll release it on Friday then. Homework assignment 2. And then today we will be discussing I think this will be the third type of method that you could use to get your wave function without having to solve directly the Schrodinger equation. So let's just start by looking at the classical picture. So let's just say that maybe you have some potential, say this will be V of X. Okay, it's maybe doing something like that. And then you have some particle and it has some energy E. So if you just look at the classical picture, so at the moment we're only focusing on the classical picture. So you know that E will be given by P squared over 2M plus V. And now if you solve, you get that P squared over 2M will be given by E minus V. Now, if you're just looking at this entire picture from a classical point of view, this is the kinetic energy, right? So it doesn't make sense that the kinetic energy can be negative. Say maybe you're just standing on the floor and then you throw a ball, right? At one point, the kinetic energy becomes equals to the potential gravitational potential energy, and then this ball then falls down. So if you had given some initial kinetic energy, there is no way that it can be found maybe 1 kilometer above the ground. So there are certain regions that are non-classical, and the only classical region that you could find that point was this point here. Right? So similarly here, the kinetic energy can never be negative. So this has to be always positive. So the classical region will correspond to E being greater than 0 classically. And this will correspond to these regions here. And then this point here these 2 points here then will correspond to the point where v equals to e. So v equals to e, similar to if you were to just throw a ball up. This is the that point that k equals to v, kinetic energy equals to v. But you can go ahead and find what is the you can also think of this in terms of the momentum. So the momentum is just given by 2 e minus v. So classically, the momentum cannot be a complex number. It's always a real number. Again, you get region corresponds to E being greater than, did I write E greater than V? Right? E minus V has to be positive, so E has to be greater than V. But quantum mechanically, you know that you'll have some Hamiltonian H psi, and this will give you an E psi. And or if you write as a differential equation minus h bar squared over 2m d2 over dx squared psi plus v psi equals to e psi. So quantum mechanically, you have this second order differential equation. So assuming that that the potential was a constant, we did this in chapter 2. So you know that, let me just guess. So you know that you can solve this in this classical region when E is greater than V. You know that if V was a constant, then your solution will be given by some constant E to be I plus or minus, and this is what some of you did for question 2. You just had Schrodinger equation with some constant, and then it's given by that, where this wave number k will be given by square root of 2me minus v. So this is quantum mechanically, but quantum mechanically there is no problem if we were to replace, if we were to have e minus v to be negative. All that will mean will be that k will be negative. So we take the square root of 2m v minus e, and then this thing sitting inside the square root will be a real number, real positive number, and then you're left with the minus 1. So these regions are not classical, but quantum mechanically they will be allowed, and they will give a simple example of alpha particle decay. But if you were to take this and plug it back into that mathematical solution, then in this case it means that psi non-classical would be A, E plus or minus. Now this is just an I, right? So you get I, but there was the other I, square root of 2m e minus v in bracket multiplied by x, right? And this, we did this, I think we did this in third year, so this gives you plus or minus kappa. And so these were oscillatory types, these are just decaying modes, and the decaying mode responds to E minus V being less than 0, and these were the non-classical regions. So the idea behind the WKB method is that those one-dimensional problems that we solved, where you have things like, so let me just repeat. So if V is a constant, what you found was that the wave function was just given by A, E, I, K, X when this was in the classical region. If now it was going to be given by psi A, E plus or minus, which for there I will call these types decaying modes, Kx. Right? So the idea behind the WKB method is that what will happen, say that you have some V, but unlike here where V was a constant, let's say that it's very, very slowly with respect to X, right? This will mean that you should be able to approximate your wave function by either this type of functions or those types of functions. But if you just look at the Schrodinger equation, so the Schrodinger equation h bar 2 d2 over dx squared psi plus v psi is given by e psi. This thing, in general, the wave function, it's a complex number. So it will mean that you should be able to write this complex number in that form. But let's just say that it will have some amplitude. But now that a will be depending on the position. This is the new thing, whereas the a was a constant. So we just say that, and also the phase. So e I, but you're not sure whether it will be in the classical region or non-classical region. So you're just going to call the phase by letter phi, but now it will be depending on x. And the first thing then would be to try and find what this a and phi would be. So to do that, you plug them into the Schrodinger equation. So let me rewrite the Schrodinger equation as d2 over dx squared psi will give you 2m e minus v over e bar squared. So let's just write it like that. But I think I did say that if when I was just discussing the classical picture, p is given by 2m classically. If you saw what p was classically, p was given by that. So this could also be written as minus p squared over e bar squared psi. Remember that we've just made an assumption that psi will be of this form. So what then we do, take this form and we try to plug it into the Schrodinger equation to see what will happen. Everything I'm saying is written in these slides. So the last thing that I said was that we just assume that our wave function will be of that, and I have to emphasize that this is depending on x. Then we take that and we plug it into the Schrodinger equation. So let's see what happens when I plug this into the Schrodinger equation. I'll just first use a version of the Leibniz rule. So if you have two functions d2 of d, so this you can check that this just gives you d2f over dx squared g plus 2df over dx dg over dx plus d2g over dx squared multiplied by f. Right? I think everyone should be able to prove this. And then we apply this to our, it's called a guess. So we have guessed that our wave function will be a product of a, it's a function of x, multiplied by e I phi of x. So we just have to apply Leibniz rule to that function. So this gives, so it can add there. So we get d2 over dx squared a of x. We'll still have ei phi of x plus 2 dA over dx. Then now, right, I'm looking at the term, so you have to differentiate the exponential. When you differentiate, you bring down an I phi, ei phi, plus a of x, and then you differentiate the exponential twice, but you've already differentiated it once there. So you just differentiate that again, so you get I phi squared ei phi plus a of x, and then now you differentiate there, so you get I phi prime. So by the prime derivatives, I mean derivatives with respect to x of e phi. So this is just the Schrodinger equation, which I wrote that this should give you minus p squared over h bar squared, which is real, multiplied by the wave function, which is a of x ei phi of x. And because the exponential, we will assume that it's not zero. So this will imply that you can cancel it out everywhere. Right. Now we have assumed that a and phi are real constants. So this equation then will split into real and imaginary part. So the imaginary, okay, the real, let's just start by the imaginary part. So on this side of the equation, there is no imaginary part. Is real, h bar squared is real, a is real. So the imaginary part will give you the equation 0 equals to. Then you just look, this is imaginary because of that I. So you get 2a prime, there is nothing left, plus the other one that will be left will be this I here, right? So this will give you a, and then you have an phi there. So this is you will get two equations, right? We're just saying that the imaginary part of the left hand side equals to the imaginary part of the right hand side. There is no imaginary part on the other side, so you just get this equation. And this equation, everyone happy that it looks to me like a prime. I think I'm missing a phi. 2a phi. There's a phi here, right? There's that phi there. So this looks like a prime phi prime. Just think this equation, I think a squared. Right? So is everyone happy that if the, and by prime I mean d by, so what I'm saying is that this is d by dx of a squared phi, right? So if it hits the a squared, you get 2a phi a prime, which will give you that term. So there's a factor of a there if you want, but because it's 0 and a is not 0, so if it hits there, you get 2a, that a there, a prime by chain rule of phi, and then once it adds on the second one, you just get the phi with a squared, but I've got out that one. So this equation, it's not that it's equals to that. There's a factor of a somewhere missing, but we are assuming that a is not 0, so we can leave it out. So we end up with the first equation just gives us a squared phi derivative is a constant. So let me repeat what I said. So you ended up with the equation a squared phi prime. So let me write everything out. Is equals to 0. So what is a squared phi? Remember that we're trying to find what is a and what is phi of our very clever guess of in the WKB method. This equation is easy to solve. This just means that a squared phi is a constant. So first equation just gives you that a squared phi is just some constant. So this means that I can solve a over, I've taken, it's just some constant, take the square root, so a will just be the square root of phi of x. It is, and then the other real equation that you will be left with will be the one. So if you remember, there was a term coming from differentiating with respect to a twice. Okay, so I cannot hear you. Okay, can everyone hear me? Oh, I'm reading the first chat, so I think everyone can hear me by now. So the question was, okay, are a and phi real constants? I think that's a good question. So if you remember solution to the Schrodinger equation from chapter 2, this was a real function, and k was also a real function, but we had assumed that v was a constant. Right? This is what we did in chapter 2, or that if you remember, we might have been given a problem like this with the energy being there. This might be v naught. V was always a constant. It's either 0 or v naught, and then you solve it. And in that case, a and phi, so phi will be that phase were real constant. But the new thing with this chapter is that we have that v is not a constant anymore. So we have made the assumption that psi, then if the function is not really varying that much as a constant, it's a function, but it's not really varying that much. So it will mean that we can still make use of wave functions of that form. But now we have a as a function of x because of this new thing here, that v is no longer a constant. So we are assuming that e and phi are not real. There are real functions, but they are not real constants. Right. So then the second equation then will come from looking at the real part. So the real part will only have d2 phi. But again, because we are assuming that a, although it's not a constant, it's slowly varying. So the first derivative will nearly be 0, but by the time you get to the second derivative, these terms will be 0. So the only term that you will have to look at will be a phi prime will give you minus p squared over h bar squared a, and the a's are going to cancel. So then you get that d phi over dx is given by minus p squared over h bar. So this means that you can solve for phi. So divide by dx gives you that. So phi of x is a function. I have to emphasize that it's a function of x. This will give you a, but a we have already solved is c divided by p of. I think I should just erase. So what we are finding is that we have this equation, and we can then solve that equation for phi. And the solution to that equation, if you just read it off, is phi. So this is when you look at the real part of the Schrodinger equation, you get the equation that phi of x, once you solve it, you get plus or minus 1 over h bar integral dx p of x. So our full wave function then, psi of x, will be c over square root of p of x. Right, so this is what I called a of x times e, and then phi I just solved is given by plus or minus integral dx p of x. And here we are still in the classical region, given e smaller than v. So again, we're still in the classical region. So there is no quantum tunneling or anything. So this is the final result of the WKB method. Because the Schrodinger equation is a second order differential equation, this will mean that these have to be linear combination of those two. So everything is included in the notes. So let me just recap what I've been saying. So if now that v of x is no longer constant, you can still make a guess of what your wave function looks like. So it will be, this again is not a constant, a of x, ei phi of x. Then you take this and you plug it into the Schrodinger equation. The Schrodinger equation will split into two equations depending on whether you're looking at the real or the imaginary part. So this you don't have to do, just use the Leibniz formula directly on the wave function, which is a product of A and EI phi. And then you group the terms that have i's, which are the imaginary terms. So those terms have to be 0. And then the other terms have to be, this is minus p squared over h bar squared, A. So then the imaginary part has to be 0. The real part has to be minus p squared. So you end up with these two equations. The first one, rewrote this as something like d over dx of a squared phi. This equation is easy to solve. This just means that this is a constant. And then you can solve for what A was. And the second equation, you then solve for what phi is. And I think you will find that phi prime is P, which is why now I'm writing that as a P. So the phi prime is given by P over h bar, plus or minus. So this means that the amplitude A of x will be given by C over square root of phi prime. So this is C over square root of P of x. So you have that part there. And then the other part, you've just solved for what phi would. This is just a simple differential equation. So phi is just given by the integral. I mean, this is just the phi over x is given by P over h bar. Phi is given by P over h bar dx. Integrate, so phi is just integral. But there will be constants of, if there are constants of integration, you can always absorb them into this undetermined constant C. So your final result of what we've been doing so far is that the wave function approximation in the WKB is given by this function. And you don't have to go through the derivation every time I give you a problem. Just you can go directly and try to apply it there. And this holds because again you say that plus or minus I, so these are what I call the oscillatory types, meaning that again we are still in the industrial region. So as a simple example of this, we will apply this to the infinite square well. So say you have an infinite square well. So your particle is always bounded classically to move between this region 0 and A. So it has to be found somewhere there, but it cannot be on this other part here of X. It cannot be there. So let's just say that then you're just given some function V, which is just some function of F, right? F of X, and we don't really know. So if we were then try and apply this directly, even though I wrote it schematically, this just means that the wave function can be approximated by 1 over square root of P of X. So this term 1 over square root of P of X is the A. And because the Schrodinger equation is second order differential equation, so there will be two solutions. So I'll denote them by C plus EI phi of X plus C minus EI phi of X minus that. And then these exponentials, you can write them in terms, you can just use the Euler formula. EI phi is given by cos phi plus I sin phi. You can also write this would be an equal sign, E1 over square root of P of X of C. Maybe use a different one. Say I call C1 out sine K, not K, because Kx will be the time when we're dealing with the constant, but now V is not constant, right? And plus C2 cos phi of X. And because we are still dealing with this simple type, so whenever you have vertical walls, I'll come back to what happens to these turning points when the walls are not vertical. But whenever you have vertical walls, right, it simply means that because the particle cannot be outside, it means that we have to impose a condition that psi of A has to be equal to psi of 0. This has to be equal to what? Let me just start with phi of 0. So phi of 0, if you recall, there will be some constant, amplitude constant, and we have to integrate from 0 to x, if this was an x, of p of x dx. If you set x to be 0, so what is phi of 0? So the phase evaluated at 0, integral from 0 to 0 is what? This is 0 because the area is like integral from a to a is 0. The wave function is phi a constant. Is phi a constant. Phi is not a constant, it's a function of x, but it's a slowly varying function of x. Phi and a are not constant. They are constant for chapter 2, but where the, so for example, if I had given you this function and specified that this function was just v naught, which is what you did in chapter 2, then phi is a constant, and a, the amplitude, is also constant. But for this case, it's not. So the function, maybe I just gave you some function as the potential v. It's not a constant, but we have derived a formula, an expression for it in terms of, so we derive this phi of x given by integral of p of x. It's not a function, it's not a constant because there's an x there. And now I said that x, so be 0, so maybe we should call this, or maybe I should call this dummy variables. The x is sitting there, right, which is this x. But now I'm saying what is phi of 0. So phi of 0 doesn't matter what it is. We're integrating from 0 to 0. So this is automatically 0. It's not a constant, it's just that at that point there, it's 0. Then psi, which is the wave function, not the phase, again, is a phi obviously is not a constant, but at 0, you don't want your, so psi squared, given that psi squared gives you the probability of finding the particle, you don't want to find the particle outside of these walls. So at 0, it has to be automatically to vanish. So this means that if you look at the wave function has to vanish 0, phi 0, phi 0, and phi 0 I just said it's 0. So sine, this is 0, so this gives you C2 has to be 0. So this means that the wave function for the infinite square well using this WKB method is just, let's say 1 over square root p of x. There's still some constant, which I called, I think, C1 of sine phi of x. So phi is not a constant, and again, the amplitude is not a constant. Maybe if you remember from first year, these things might be doing something. So the amplitude is not a constant, and also the phase. I mean, if you were thinking of it in terms of wave, if this was first year, it was doing something like this. A is a constant here, and also the phase, because the phase is related to, but your wave could be doing something, might be that the change But we just assume that these things are not constant, but they are slowly varying, which is part of the reason why, for example, d2a over dx squared was 0. But for now, we've just shown that for the infinite square well, phi of x is just given by that expression. Then you repeat. So let me ask again. So if you have the infinite well, what is phi at a? So this is a, this is 0. So what is psi at a? And I've just shown that the only remaining thing would be some constant over square root p of x. And then you get sine phi it's being evaluated at a. Right? This what is the wave function evaluated at a? Yes. 0 because the particle, this psi squared measures probability, the particle cannot be outside, so this has to be 0 at a, meaning this wave function has to be 0. So this again gives you the condition that phi of a has to be equal to n pi, and phi of a, if you remember, is when you look at so 0 to a, it's a function, the x is usually sitting there, so now there of p, maybe dx prime, that this has to be equal to n pi. So this looks like the Bohr-Sommerfeld old quantum mechanical quantization condition, but let's just go ahead and use it for the infinite well. So we've just shown that phi of a is given by integral 0 to a of p of x dx. This holds for any general function. This has to give you n pi. Okay, let's just go and apply it when to check if our results make sense. Let's go and apply it for the infinite well, where that function is just given by 0. So the standard well. So in that case, it means that v equals to 0, which is a constant. Calculate p. So p is given by square root of 2me minus v. And in general, these would be functions of x, but now we've just said that this is 0. So this gives you square root of 2me. This will just be a constant. Then you plug it there, so you get square root of 2me multiplied by integral from 0 to a of dx. This gives you square root of 2me. A, this gives you n pi. So you can solve for e and look. Using this WKB method, you've just shown that e is given by n pi squared. I think that's 1 over h bar. So h bar squared over 2m a squared. And this, if you remember from problem 1, this is what we showed in section 2 for the infinite well. So we are able to show that the WKB method works for this simple problem of the infinite well. So this in general, this is what I've been saying. Then you go and you apply this, see, there was this 1 over h that was missing, but once you put it back there, see, you can then reproduce the classic result. So everything that we've been doing so far has been the So the classical analog will be EIKX. These are the regions, the classical regions where you have some potential, where you have E minus V is positive, so that the kinetic energy can be positive, or E minus V is positive, so that the momentum can be real. So these are the classical regions. So this region here is what is classical. But now quantum mechanically, there is nothing stopping us from having E less than V. Right? And if you just do what I did there, you have I, let's say I square root 2m E minus V of x. These are now functions of x, right? But now if you look, E minus V is the one which is negative. So you can, or meaning E minus V. So you can factor out a minus 1. You're left with 2m V minus E. V minus E is positive. So the I, this I, that I, then changes the factor of plus or minus IH there. So in this new region, you can try to do the same thing to derive it, but in the non-classical region, this is the equivalent of you having the second one being e to the minus kappa x. So this gives you, let's see, e to the plus or minus 1 over h bar. And as I kept saying that you wanted this thing, v minus e term, to be positive, so you have to be always make sure that you are taking the mod, the same thing there, so that these are just oscillatory. So this is what happens when you are in the non-classical region. Right. So we will try to apply this to these types of simple problems. So let's say that you have a region. Right. But let's say that your potential is you have a very high potential barrier, right? So on the left, you will have a wave coming in and it will get reflected. And maybe there might be another wave going, so I'll label that as A, this as B, this as F, right? So this will mean that, okay, let me call this region 1, region 2, and this region is the let's say that maybe your energy is just there, right? So classically, your particle cannot be in this region because it doesn't have enough energy. So this is E. It doesn't have energy. It doesn't have energy to get through this region. But what I will show is that quantum mechanically, although there might be some possibility which is decaying, that the particle will actually be found in region 2, which is the non-classical region. So in region 1, your wave function there, psi1, we've done this before, so it's just going to be the wave moving to the right. So this wave will be given by E ikx plus B E minus ikx. Similarly, in region 3, so psi for region 3 will be given by F E, and it's moving to the right, so E ikx. So plus refers to waves, right, moving waves, negative to waves moving to the left. But we want to know what will happen with this region here, right? So because that's a non-classical region where you have a very high infinite potential barrier, we make use of the WKB approximation. So you get C over square root P mod of P of X E 1 over H bar P prime dx plus the same thing, new constant E to the minus I over H bar. But because this is positive, And it might be that your width, like this thing here, it might be that it's actually very large. So over that region, if this p, the x term here, which is always positive, keeps growing, this seems to be growing up, and we don't really want a wave function that keeps growing up. So the only way to prevent this from growing up will be to set this c to be 0, so that inside that region of width w, the wave function is given by d e to the minus of something positive. And yeah, maybe I should use this picture. And what you are interested in is that you are looking for the transmission coefficient. And I'm not sure if you remember, but finding this, I think it was a square, took time because you had to solve the Schrodinger equation in region 1, try to match it with what will happen in region 2, then try to do it for f. And given, and if this was not infinite, then you ended up with very messy expressions. But we are just going to make use of the WKB to get this transmission, then apply it to alpha decay to nuclear type physics problems. So let's see. So I've just argued that in the tunneling region, your thing is just given by C, maybe not C, I think it was D, but it has to be e to the minus 1 over h bar integral p dx, right? And let's see. And the claim then would be that f over e is given by that other coefficient, which is just e to the minus of once you square it, right? We're looking at the transmission coefficient is given by t over f, f over a squared. So this would be that gamma, and in this case, gamma will be 1 over h bar integral. What I showed was the only thing that was missing. So the transmission coefficient, you don't have to do all those matching things there, matching things. You can show that it's just given by e to the minus 2 gamma, where gamma is given by that. And one of the first classical, I think this is what I was trying to say. Classical application of quantum mechanics was to the alpha decay. So for alpha decay, you have, let's say that you can look at this picture. So you have maybe an alpha particle. You might think that because this is positive and that's positive, that this might be repelled and then it might leave the nucleus. However, this strong nuclear force, which is actually quite strong and it's very attractive. So this thing is always bound, and unless it has enough kinetic energy or energy which is much bigger than there, so that it can move into this region. So it will never be in this region. So this region classically are forbidden for the alpha particle to be found in. So what Gamow did was that he modeled the nuclear force as just some very strong infinite potential well. So the particle classically has to be here in this region. But if you measure things experimentally, you always find that the alpha particle seems to be escaping or tunneling outside of its classical region. And what he wanted to do was to try and calculate this type of decay. So you know that this transmission coefficient will just be given by e to the minus 2 gamma, and energy is given, it's just Coulombic energy, so 1 over r squared. So if you're going to apply the WKB method, you have to calculate 1 over h bar of the momentum, and you know that the momentum is given by 2m. It has You remember that it's usually E minus V, but I've changed things around because this is now negative. So V minus E, the one which was positive. So let me just start with V. So V is just Coulombic interaction potential. So you get 2E squared over, but let's just focus on the parameter. You'll get this 1 over R. I think this has to be R. And then you subtract some E, right? So the integral that you end up having to do will be something like root R2 over R minus 1. Right? And how do they get this? Is the transmission coefficient for related between? Yes. So they are related and also related to the half-life. So once you have, okay, which I will show later, but for now we are stuck with having to calculate this phase in the WKB method. So let's see. Okay, let me just share the whiteboard and then I'll come back to these ones so that we can quickly go through that integral. So we just want to find maybe between R1, R2, integral R2 over R minus 1. So the suggestion is that you make so you say that R will be given by R2. I'll do this very quickly. So find squared U. So the R will be given by, say, 2R2 sine theta, sine U, cos U du. So then this integral then becomes, let's see, R1, R2, square root R2, or so everyone happy that this is, well, I get sine squared minus 1, and then I'm left with 2R2 sine U cos U du. Right, so this gives you sine squared U. 1 minus sine squared U, this is cos, so you just get square, and everything is inside the square root, so you get cos U over sine U, 2R2 sine U cos U du. The signs cancel, and by now everyone can do this type of integrals, right? Because you did them in the first exercise. So you use half, I think it's 1 minus cos 2u integral. So this gives you half u minus, this is again another half of sine 2u. You can solve it from there, right? So everyone happy that r over r2 is sine squared. So if you take this square root, this gives the, so what I'm saying is that this gives you sine u, but you don't have sine u, you have u. So u will be sine minus 1 of r over r2. So then this can simplify to half sine minus 1 r over r2 minus half. And then this is just 2 sine u cos u. Sine u is given by square root of r2 over r1. Just r over r2. And then the cos gives you the square root of 1 minus r over 1 minus sine squared. So this gives you r2. So this ends up with an square root of r2 minus r, which is sine minus, just remember the final expression. So you will get sine minus 1 term, then you get the other second term, which will be square root r2 minus r. Right. And if you look at the slides that I shared slide, so that I did it very quickly, but you just do the trig substitution. then get an integral over cos squared u. You know how to do that. Then replace these u's and sine u's in terms of the original variables that you can get by solving this one, by solving the original thing that you did there. If everyone is not clear about this, we can go through it again during the break. Let me go back to the slides. Which are not sharing again. Taking too long. So as we wait for the slides to reappear, I think I have to stop sharing the whiteboard first. Share files. So now that we have applied it, and you should have seen that for most of them, the wall, I mean, even for the tunneling effect for the alpha decay particle, I might as well use the whiteboard because I'm unable to go back. So you'll end up with that the tunneling effect for the alpha particle will be given by, might be sine minus 1 square root of maybe R2 over R1 minus R2 minus R1. This is the square root. And then you make the approximation that R2 over R1 smaller than 1. So then you can then make use of the expression sine epsilon is approximately equals to epsilon. And then you will end up with the expression that was given in the slides. Right. Okay. Are there any questions so far? Because I think it's the same problem I had with the first lecture. Can't seem to go back to the slides. Are there any questions so far? Just unmuted. So to summarize, the idea behind the WKB method is that you tend to look at this type of things that you were this scattering type of things. So you are going to make some guess that your psi, these things always worked when V was a constant. So you again want to make use of these things, but now A, the amplitude will be depending on X, and also that sort of K part there. So we just made that this was e to the I phi of X. We plugged this into the Schrodinger equation, and then we were able to solve what was A and phi. And then we applied this to two types of problems. So we've applied it to the infinite square well, and we checked that we were able to reproduce the results that we have reproduced either by solving the Schrodinger equation directly, or by using the variational method. And then the other problem was that we applied this WKB method to alpha decay. Now, obviously, the nuclear force is much more complicated than this, but what Gamow was able to find was that his model was very quantitative and quite useful. However, now we have another problem, which is that in everything that I do, so even if you look at the infinite square well, I'm always assuming that the walls are vertical. However, in general setting, the walls are not really vertical, so you might have, you don't really know what's happening at the classical turning points. Right? So at the classical turning points, which is, so if you throw something, it's the point where the kinetic energy is the same as the energy. The problem here is that, okay, let's just see what is the problem when at the classical turning points. If you look at our expression, so even the one that I just wrote now, there's a 1 over square root of p of x. And if you look at this is square root of 2m e minus v, right? So at the classical turning point, right, this, okay, what is the problem? So the turning points corresponds to the case where, so this was a plot of v and e. They correspond to the point where e the same as v. But if you plug into the expression for p, so these things then become infinity. So you cannot really match the, you've done this type of matchings where you have your wave functions being given in two regions, and in those two regions it's given by different functions, but you match them by saying, let's say that you look at, say that your barrier, I'll put it at x equals to 0. So you have region 2 and also region 1. And to move from, say, in this region, maybe this was the, let's say, non-classical, classical, or vice versa. In order for you to move from one to the other, you had to match them. But you cannot do that because in order for you to do that, you have to start putting E equals to V, and your wave functions will then go like 1 over 0. So you cannot do that. So the way that you solve this then would be, so at the classical turning points, E is approximately equals to V. So, however, I could have said that V as a function of X, right, is given by, then I just do a Taylor expansion, right? I know that V at 0 at this turning point is given by E, but I could just see what happens when I include the other first order correction from the Taylor expansion. So I know that this will just give me X multiplied by what? Let's see. So this is just the usual Maclaurin expansion, right? So this has to be V prime 0. So it's like, I don't know, because if I was just to try and go ahead and try to match the two things, I will find that I am unable to do that because of this 1 over p of x, which keeps blowing. This keeps going to 1 over 0 at the turning points. So I just move slightly away. So I just approximate this by that. So now we then try to plug this into the Schrodinger equation, d2 over dx squared psi plus the potential, which is not given by, and v naught, it's E. So you get E plus x v prime 0 multiplied by wave function psi. This gives you E psi. I think this E will cancel that E. So I'll call this, it's sort of a patching because I want to move from region 1 to region 2, but I cannot do what we have been doing in chapter 2, where we just set them to 0 and try to compare because this blowing up of the denominator. So you then just say that, well, the problem is arising from E is approximately equal to V. So let me just move slightly away or consider the next term of the expansion and then plug that into the Schrodinger equation to try and see what this patching wave function would be. So the e's cancel and you're left with d2 psi over dx squared will give you 2m over h bar. I think maybe everything will be on the slide, so if I get, but the point is that you get, it's a plus because you took this plus x becomes minus, then you still have to multiply by that, so you get v prime, right? And with an x, I can call this parameter anything, v prime at 0. So it's wise to call it alpha cubed. It's a constant, but you will see why I called it alpha cubed. So you end up with the Schrodinger equation for your patching function. It's given by this function, this differential equation. Then you can rescale your parameter because if you look carefully, you have d2 over dx squared psi given by alpha squared alpha x psi. Right. Alpha is a constant, so you can take it and put it there and informally plug it. So you end up with d over d alpha x squared of psi equals to alpha x psi. And you think this is alpha squared, right? It was alpha cubed. So so what should we call it? Right. You can call that z because then your differential equation, it's like people who tried using Hermite polynomials, the same trick that we did with the Hermite polynomial. The thing that we had to work initially was working with was x, but our differential equation was, it had these things multiplying around. So you switched parameters to this zeta, which is given by m omega, I think, over by h bar x, I think, with a 1/4. The solutions are expressed in terms of this parameter, but the original one was this one. So we are doing the same thing here. Dz squared is equals to psi. And has anyone ever seen this equation before? It's the famous differential equation. It's called the Airy differential equation, and you can look it up. And again, because it's and these functions are usually denoted by AI. In this case, it will be say. And because it's a second order, there are two Airy functions. It's just that usually the one with the nice parameter is the one that people label as AI. Yes. So this means that the patching wave function, we have solved it. So the patching wave function, it's just given by it's a linear combination of the A function. So psi patching is given by a Airy function plus b Airy function. But we still have to determine what then these things are. But now this wave function psi patching function, unlike the other one, which had this 1/p of x, which was problematic at the turning point, this function is not problematic, so we can match. And if you look, so we have this point here, which is the turning, but there will be points that are far away. So let's say that I'm calling this Z. So you will look at Z, which is far away from 0. The area function has an asymptotic expansion for large Z. I think it's going to be given by maybe e to the minus Z, maybe 3/2. And then it also has another asymptotic. So there are asymptotic expansion for these functions. So we are going to look at regions that are either very far, very near, and then try to match them. So I think this might call this region 1. This might be region 2. And this you can call the turning point region, which is the region in between them. So by just using that patching function and matching your, okay, let me just summarize what I've been saying for the past. Our problem was that we couldn't just take it to be going to 0. So then we suggested that we first looked at this point here, but because our problem was that we were saying that E is approximately V, we just looked at it away from, slightly away. So if we are looking at it slightly away, then we can make and X is approximately equal to 0. We're looking at points close to 0. So this might give you V of 0. V of 0 is just E0, or that E, right? And then plus X V prime of 0. Then you take this V, plug it into the Schrodinger equation, and find what this sort of patching function, patching wave function would be, which is what we did. But before we did that, the Schrodinger equation just reduced to that. Then we changed parameters, so that alpha squared went there. You're left with only alpha. Alpha is that. Change parameters to Z, and then you find that this differential equation, if you look it up in standard mathematical textbooks, this is the area solution. So that now we have to match to find what these constants A and B are, which is what then we were trying to do. But before I go there, as I was saying, the area function, it has an integral, nice integral form, but for what we want to do is that we want to look at Z, maybe Z going to infinity, and also maybe Z going the other region, which I called 2, and then we're just going to make use. So our patching function is given as maybe A area of Z plus B area of Z. So we are going to look at either this condition or that condition, and then try to match it with what we got from the WKB variational method. You can also plot it, but we are just only interested in the matching. So in order for us to, so we found what this psi p is, but in order for us to plug it into the WKB method, you needed to compute this other part there. So phi, if you recall, is given by 1 over h bar, integral from 0 to x of p, maybe with a mod there. But this simply means we have to find what the momenta is. So the momenta, if you recall, is given by 2m e minus v. But now v, we have approximated to be v0, which is e plus x v prime of 0. This is of 0. Right. The e's cancel. And then, yeah, this is definitely 0. And then you're left with, and this is inside the square root. So there might be some factor that I still need to check. But the point is that it's just a constant there, but you're left with this in here. Oh, I see where the 3/2 comes from. Everyone would be that you're going to get minus x, but there is an alternative giving you 2m v prime of 0, maybe h bar squared. This, and this, if you look, this is how we defined our parameter alpha. Maybe it's just check that it's 3/2. So you know that the momenta, which is what you need to plug into the phase, is then given by h bar alpha 3/2 square root of minus x. You are going to do the same calculation, but for, remember that we are looking at x, or what I'm calling z, very far, which is positive or negative. When it's negative, then the integral just changes from x to 0, but you follow the same thing. So let's just consider this region. Right. So once we have P, then you can go ahead and find what is the phase, 2 factors of h bar. Everyone can do that, right? So it's x half and 1, so you get x 3 over 2, 2/3, right, which is that. Remember that we want to plug this into the right, we want to match this, right? So we just calculated that the phase, like phi, was going like x 3/2. The momenta we calculated, I think we found it to be square root of x. So when we take the square root, so saying that p, we found p to be x to the half. So the square root of that gives you 1/4. The thing sitting there, there. So this is the wave function by WKB. Then you have to match this with the, so remember that it's given by D, E, and then the other part here was given by A area function, in a combination of the area function, let's say B, B, I of Z. Then you have to try and match these things, and you're looking at regions that are Z away or x far away, and then you just use that table, and it will be going like this exponential, that exponential. I think this is probably b. Then you match them. Now you can go ahead and match what you find for the area function. So I think this is a typo. Maybe this was a plus, and again this is, I think, a b. So if you see, there is no O. So if you want, there was a C which was going like e to the plus something, but we set that to 0. So this means that this B is also 0. So the only thing that means that this has to somehow be equal to that one. And then we can get the A that is appearing in the pitching function. And then now we do the same thing for the other region, which is far, far away, negative. Like, but in this case, the A functions do not behave like exponentials. They will be behaving like trig functions. Let's just see. This. And then you match it with what you had from the WKB with A and B, and you just match. But D you had already gotten once you were matching the region which was Z greater than 0, far that region there. So you can plug that, and then now you have what is C and what is also D. So if you have those that are not vertical, then the connection, or the things that will be connecting, these are called connection formulas, then are given by those expressions. And I think maybe I think for today I will end here. Just I don't have references for area function, but just look at properties of the area function. Then what we did was we just said that E approximately equals to V was problematic. So we looked at regions close to the turning point, close to x equals to 0. Then, so we said that v of x had to be e, approximately e plus, then we just included this term. Plug this into the Schrodinger equation, then we found that the matching function was given as a linear combination of these area functions. We call that b, and the other one was a area function. And then once we had this matching function, then you could match, and these are the results of your match. I think in the next lecture I will start by applying these matching connection formulas to some problems. Right. So I think we can end there. And then the last thing that I need to ask is about homework assignment 2. So it's either I give it to you today, because I see most people are still here, on Friday. Which day then will you prefer getting it? Friday. It will be due in a week's time, so it will be due on, let me just check the date, on the 25th. So next week, Friday. But for this one, I think because it's just application of the variational principle, I will give you the trial wave functions. So all you have to do then will be to do the integrals or differentiate. But if you run into problems, I think you should tell me which problem has which integrals you cannot do, so that I can give you the integrals. Don't spend too much time. Like on the first homework assignment, would it be possible to have the date that following Monday, since we are writing statistical mechanics on the 25th? I thought you were writing statistical mechanics this week. Which one are you writing? Okay, yes. Assignment 1 is due. It was due yesterday, I think. Okay, so I'll push the due date maybe to Monday, that Monday, which will be the 28th. But you do realize that this will mean that you will only have maybe 2 days. Yeah, so the due date then will be on Monday. So for the test, it will mean that maybe the test has to go up to and including time dependent. So you will have to write the test without having any homework assignment from that section. But at least you would have done some practice for WKB and also variational method. I won't be asking you those long. Remember those find x and d, where you had to integrate 1 over r minus r prime with a d3r prime. So those types will never come. And then for question 6, so on the memo for question 6, I didn't do it to second order, but I saw that most people were able to do that, right? So if you are still unable to do that, you can ask me next week on Friday for the consultation, or because there's a test. But I think most people can do that. But I think for the test, I won't be asking that type of question 6 type of thing. But it could be it's examinable. It's a good problem to be able to do. Right. Okay, I think then we can leave it here. The test is 24-hour test. Same with the exam, so it will be 24-hour test. But the problem with this 24-hour test is that some students ask other people to do the stuff for themselves. But I think it's fair that people are mature enough that they are not going to be copying or asking other people or online tutors and stuff like that for the solution. So it will be 24 hours, and I'll try to set problems that. So I won't be asking like X4 because X4 I think most people have done that. It might be new types of problems. So it will be 24-hour, the same 24-hour for the exam. And it will include the stuff that we still have to do for time-dependent perturbation theory. And then the exam will cover everything.
Sorry, sir.
Yes.
So for assignment two, is it possible for for us to have the due date on the 28th? Then we still have about 3 days before the test to go through the memo, because then you're kind of still preparing for the test on the work.
So you're asking that the due date should be on the 28th, right?
Yes, please, because everyone said, or the poll said that the semester test is on the 1st of July.
Right. So the due date for second assignment will be on the 28th, and
Okay,
then
thank you.
the. Oh, all right. Yeah, I'll give you the results of the poll. So the test will be written on the 1st of July. Not. So due date for second assignment is 28th. Then you write the test on the 1st of July. Okay, I think that should be clear. Right. I think I'll stop the recording in case you can ask me anything after this.